Cisco instructor Andrea here. In this video, I'm going to review some important aspects of IPv6, specifically address structure for IPv6, subnetting, and address types. First, we'll look at the IPv6 addressing structure. It's important to realize that IPv6, unlike IPv4, is made up of 3 sections. If we contrast that with IPv4, which is made up of 2 parts, the network part and the host part, with IPv6, we have 3 parts. We have the global routing prefix, and the global routing prefix is typically made up of 48 bits, or the equivalent of 3 hextets. And remember, a hextet is 16 bits. That's how we're looking at this. The X's would represent a bit. 4, 8, 12, 16. So I'm going to have 3 hextets, and those are going to be representative of the global routing prefix. The next section of an IPv6 address is the 16-bit subnet ID. Unlike IPv4, we will do the subnetting within the IPv6 address in the 4th hextet. And this is, again, just representative of 16 bits right after the global routing prefix. Next, we have the unique identifier. The unique identifier is the interface ID. This will be the part of the IPv6 address that represents each host or each end device, or the IPv6 interface addresses, and they're going to be unique. This part of the address is going to be 64 bits. If we break this down, the first part of the address, the 48 bits plus the 16 bits, that's representative of like the network piece. Whereas the last 64 bits is the interface ID, totaling 128 bits in our IPv6 address. Important information and terms related to IPv6 addressing is there's 128 bits. It's written in hexadecimal, so there's 16 values in IPv6, 0 through 9, and then A, B, C, D, E, and F. There's 8 hextets that make up an IPv6 address. 1 hextet equals 16 total bits. Here's an example. 2001, ABC1, each of these is called a hextet, and each hex value is 4 bits. That's how we get up to the 128. Each value in the hextet is called a nibble. As an example, if you look right here, this is a nibble. It's 4 bits. There's our next nibble, and then another, and then another. So 4 nibbles make up a hextet. The combination of the global routing prefix and the subnet ID is the equivalent of the prefix length. The prefix length is similar to what we studied with IPv4 for that slash notation or the subnet mask. Here, as we look at the /64, the only difference is it actually represents the global routing prefix and the subnet ID. If we combine those two, that's what our /64 is. Typically, an IPv6 address will be a /64. I get asked a lot of times from students, will it always be that? And actually the answer is no, it won't always be that. However, that is the way we teach it, and that's fairly standard. Could it be different? It could be, and that would be something we can address in another video. Because IPv6 addresses are so long, IPv6 uses the rules of compression in order to shorten them. Let's review those rules. First of all, in an IPv6 address, you can remove the leading zeros from each hextet. It's important that you only ever remove the leading zeros. You cannot remove lagging zeros or zeros in the middle of two values. Otherwise, you have no way of knowing what the order of the address is. Hextets of full zeros can also be compressed, and then you can just use a double colon to represent that hextet of zeros. I'm going to give you some examples of this so it will make it more obvious. The other thing about double colons is you can only use double colons once in an address. You may be combining these rules of removing the leading zeros and double colons. But remember, if I've got a total of 8 hextets, and if you have, let's say, hextet number 3 is all zeros, and hextet number 7 is all zeros, you can only use the double colons one time. Here's an example. We've got this full IPv6 address, and we can look here and see that there is a leading 0 in the 4th hextet. Here I have all zeros in the 7th hextet and 2 leading zeros in the 8th hextet. These are the zeros that we can work with and use our compression rules. Here would be an example of just removing the leading zeros. Right here, I've removed the leading 0. And then right here, I've removed the 3 leading zeros and I've left 1 0. And then in this last hextet, I've removed the 2 leading zeros. This is actually the preferred way to do IPv6 addressing, is to remove leading zeros. And the reason is because then we can still see the full 8 hextets. 1, 2, 3, 4, 5, 6, 7, 8. It's a little less confusing, especially for people that are not accustomed to working with IPv6. Here's our next example, and this is when we're using full compression. We're removing the leading zeros and we're using double colon. We've got the same locations. We've got the 0 here in the 4th hextet. We have all zeros in the 7th hextet and removing the leading zeros in the 8th hextet. So this rule is the same. We remove the leading zeros. Where we're doing something different is right here with these 4 zeros in this hextet. Instead of leaving a leading 0, we're going to replace all the zeros with this double colon. Because there's a double colon there, I know that there's a set of zeros. And then lastly, I'm going to remove the 2 leading zeros in my 8th hextet. And then here is my final outcome. And again, you can see how this is just a little bit shorter than the one before, which was a little bit shorter than the one before. Let me show you another example. We'll look at an example of removing the leading zeros, and then we're going to hone in on this double colon and take a look at that as well. Here's our example, and here we can see we have leading zeros as well as 2 hextets of double zeros. If we look at it in the preferred way of removing our leading zeros, we can see here we've removed this 0. We've removed the leading zeros from our 5th hextet. We've removed our leading zeros from the 7th hextet and the 8th hextet. This is, again, the preferred way. Now let's see how we would handle the double sets of zeros with double colons. Remember, we can only use the double colons one time in an IPv6 address. So like before, I removed the leading 0. Now, because I have 2 sets of zeros, what I'm going to do is I'm going to remove the leading zeros from this hextet. For this particular hextet, I will go ahead and use the double colons. This will shrink up my address even smaller, and then I remove the leading zeros for my 8th hextet. This gives me a little bit shorter address, and again, notice I used the double colons only one time. People ask me all the time, well, can I do it the other way as well? Of course, you can do it anyway. So we can also write it like this, where instead of removing this set of zeros and replacing them with double colons, I'm going to remove the leading zero in the fourth hextet, and then I'm going to put my set of double colons here. And because I did my double colons in the first set of zeros, I cannot do that in the last set of zeros. So I just remove the leading zeros. So I can write this address either way. Another situation could be if you have 2 or 3 hextets in a row of all zeros, you would just replace that with a set of double colons. When we look at a compressed address, how can you tell how many zeros or sets of zeros you need? Well, you count up how many are missing. We want to remember that each IPv6 address is made up of 8 hextets. Each hextet has at least 4 nibbles, which are those hex values. And the compression and the double colon rules for the zeros never change. If we keep those facts in mind, we can reverse engineer an IPv6 address. If I look at this compressed address, first of all, I can notice here that CAF, there's only 3 values. I know I need 4, so I've got to add a leading 0. So right here, I would add a leading 0. The other thing I would do is I would count up the hextets, because I see a set of double colons right here. 1, 2, 3, 4, 5, 6, 7. There's 7 hextets. I need 8. So that tells me that this set of double colons actually represents 1 hextet of all zeros. So this is another area where I would reverse engineer. Now I'm looking here and I can see, well, I have 1 0. I'm supposed to have 4 hex values in each hextet. So 3 zeros must have been removed because of the leading 0 rule. I know I need to add in 3 zeros. Lastly, I can see in this 8th hextet that I only have 2 values. I'm supposed to have 4. The way I would reverse engineer this is I would be adding 2 zeros in front of the 1 0. When I reverse engineer it, this is what I would end up with. 2001 ABAD CAFE 0. Now I have the 4 full hex values. I add in my 4 sets of zeros to represent the double colon. I add in my 3 leading zeros, and then I add in my 2 leading zeros. And now I can see what the full address would be. Here's another example. We want to keep in mind the same exact rules, and then we can reverse engineer everything. As I look across, I can see here's my first hextet that's missing a value because there's only 3 values. So I know that there's going to be a 0 in front of the BAD. As I keep moving across, I can see a set of double colons, which means I'm going to have some zeros in here. Let's count up the number of hextets. 1, 2, 3, 4, 5, 6. I have 6 hextets. I need to have 8 hextets. What that tells me is that I have 2 sets of zeros that are missing. When I reverse engineer this, I will add those 2 hextets back in. Same thing goes here. I can see that the leading zeros have been removed, so I will reverse engineer that and add the 3 zeros back in. And my 1 0, I can see once again that my zeros have been removed, my leading zeros. I will reverse engineer those zeros back in. Here's my address, and I can count up these hextets. 1, 2, 3, 4, 5, 6, 7, 8. I have the full IPv6 address written out. I've added back in the leading zeros that were removed, and now I can see what the full address looked like. Let's recap. IPv6 is represented in hexadecimal. It's 128 bits long, 8 hextets. Use the compression rules to shorten your IPv6 address. An IPv6 address is made up of 3 parts: the global prefix, the subnet ID, and the unique host. The global prefix is the part of the address that will be assigned to you or your company from your provider or your ISP. This is the part that comes from your ISP. The subnet ID is used for subnetting, and I'll be doing an example of that. And the unique host portion can either be set up manually or with static addressing, or you can use some sort of auto configuration. Here's a quick look where we have set up an IPv6 address. We've used the compression rules to show you the different ways, to show you a way to write this. What part of the address is the network portion? Remember, that's the first 48 bits. What's the subnet portion? This is where we do the subnetting, and that will be the next 16 bits. The host portion, or the unique ID, will be the last 64 bits. Add them all up, and that's 128. Remember that the combination of the global routing prefix plus the subnet ID is what makes up our slash notation, or our prefix length, and it will always be represented at the end of the address. That does it for a review of the IPv6 addressing structure. Next up is subnetting IPv6. I always like to tell my students, the first thing you kind of have to get used to is that subnetting IPv6 is much easier than subnetting IPv4. Because we spend so much time learning variable length subnet masking, sometimes students think, or people think, that, oh, IPv6 subnetting is going to be even more difficult because there's so many more bits and the address is much longer. Actually, because there's so many more bits, subnetting is much easier because we don't need to worry as much or at all about keeping and holding on to the bits and saving addresses. This makes IPv6 subnetting much easier. Remember, in the addressing structure, we talked about the subnet ID. The subnet ID came after the global routing prefix. It was the 4th hextet. With IPv6 subnetting, we use the 4th hextet to do the subnetting. We're going to manipulate those bits within the subnet ID to actually assign subnetworks. You can use any nibble within the four values of the subnet ID. And I'm going to do an example, and in this example, we're going to use the 4th nibble in the subnet ID. Typically, wherever you work, if they're using IPv6, they're going to have their own IPv6 addressing structure, and you would just follow that. Here's our example address. Notice that we have a /48, and that's because the first 48 bits is the global routing prefix, and we're going to assume that that was provided to us from our provider, our ISP. Here in Arizona, 2 popular companies are CenturyLink and Cox. So maybe CenturyLink provided this to us. Now I'm going to use this 4th hextet to do my subnetting, and I'm going to use all 4 of these nibbles, so all 16 bits, and that's going to make it so that I have a /64. I'm going to start by using the 0, because remember, 0 is a hex value. And in this example, we're using the 4th nibble. So if I'm looking at the 4th hextet, And then this right here would be my fourth nibble. Now in this network, it looks like I have a lot of different subnets. So maybe I am a large company with lots of different departments. Each department needs to have its own network address. The first subnet is going to be 0000. Now this is a 64 because remember this hextet is 16 bits. The next hextet takes me to 32 bits. The third hextet takes me to 48 bits. Now I'm using the entire fourth hextet, which is another 16 bits. 48 plus 16 equals 64. That's how we arrive at the 64 bits. An IPv6 address is a total of 128 bits. What that means is I still have a whole nother 64 bits left for the unique IP addressing of all my hosts and end devices. Now I want to figure out the next network. I'm just going to increment it by 1. And then the next network, 2, 3, 4, 5, 6, 7, 8, 9. The number 10 is represented by A. The number 11 is represented by B. The number 12 is represented by C. And I can just keep going. And then if I have more than 16 networks, I can jump over and I can start using the third nibble. I could say 1, 1, 1, 2, 1, 3, 1, 4. The good news about IPv6, I can really do whatever I want to make the subnet ID unique from another subnet ID, as long as I'm following whatever my company's policies are for addressing. This is why I say that subnetting IPv6 is much simpler. I could also have used the first nibble, 1,000, 2,000, 3,000, 4,000. I can really do whatever I want. And then notice through here, if I were to go all the way to the bottom and use every single combination, the last one would be F, 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 F. This is what makes subnetting so easy with IPv6. Let's see how this would play out in an actual network. Here's our same addresses that we just configured. We started out with the 2001 0db8 ACAD /48, and then I did my subnetting. I used the 0 in the fourth nibble and then the 1. So here's my first network. And so I'm going to give this network the address of 2001 0db8 ACAD 0001. Now remember, this is a network address. It cannot be assigned to an end device, an interface, or a host. Let's look at the address right here. We can see that PC1 has been given the address of .10. So what is it? It's 2001 0db8 ACAD 0001 00000000000000000 till I get to the 8th hextet, and it's going to be 0010. That's what it would be. So we would just give it a unique IPv6 address. Notice that the G00 interface, which is my default gateway, is being given the first usable address, just the same way we would with IPv4. I give each end device a unique IPv6 address. A good rule of thumb is to assign the first address, the first usable address, to your default gateway. If we keep going, here's our next network address. Remember my WAN links, that needs to have its own network address. So we use, now I didn't use the 0, but I just started with the 1 to make it clear. 1, 2, 3, and then I'm going to address my next network and my next network. If you've been using IPv4 and studying IPv4 with me, remember we assigned each network, each LAN its own network, each WAN its own network. We're doing the same thing with IPv6. There's a network, there's a network, there's our third, fourth, and fifth. We're just going to address so that every network has that umbrella that holds them together. What would the IPv6 address configuration look like? Setting the default gateway. So we're going to set the default gateway, right? And here's what this would look like. On interface G00, IPv6 address 2001 DB8 ACAD. There's my network, the 1::1. That is my first usable address. And then on my next network, IPv6 address 2001 DB8 ACAD2, that represents the network, ::1. And now I've got my default gateway set. And then on my interface, for my serial interface, 2001 DB8 ACAD3, that's representing the network, ::1. The other serial link would be ::2. That's all for IPv6 subnetting. I'm going to go ahead and I'm going to do an example of IPv6 subnetting. In this example, the ISP has given us the network address of 2001 0CAD B023 : 48. So we have 48 bits that we're starting with in our global routing prefix. The directions here are to subnet up to a /64. That means I'm going to use all 4 nibbles or all 16 bits in the 4th hextet, the subnet ID. Now notice here it's telling us to use the first subnet nibble for the colleges. So here's Phoenix College, Glendale College, and Mesa College, right? So these are all part of Maricopa Community Colleges. So again, what's happened here is Maricopa Community Colleges has been given the 2001 0CAD B023/48 as the starting network. Now, as the network administrator, I'm going to set up some addresses. The next directions is to use the last subnet nibble for the departments. All right, so Phoenix College. Now, I'm just going to use simple addressing, okay? And I'll use the letters for the colleges. It's going to look like this. So 2001 CAD, I'm going to go ahead and use compression here. And then B023. Now it's said to use the first subnet nibble for the colleges. So I'm going to give Phoenix College A. Okay, so Phoenix College is going to get A. And now this is going to be a /52. Why is it a /52? The reason is because right now I'm just figuring out the network address for the colleges. I haven't yet broken them down into different departments. So 2001, that's 16 bits. CAD, that is another 16 bits, which takes me up to 32. B023 takes me up to 48. And now I'm just using the first nibble in the 4th hextet. That's 4 bits. So 48 plus 4 is what gives me the 52. I'm going to get up to the 64 using the departments. All right, so Glendale, 2001. And let me just go ahead and add the 0 CAD so we can see all of the hex values. B023. Now this one is going to be B000::52. Let's come down to Mesa, 2001 0CAD B023 C000::52. Okay. Now I'm going to break down the networks a little bit smaller, and I'm going to give each department its own network address. So notice this says use the last subnet nibble for the departments. All right, so Phoenix College, it's going to be 2001 CAD B023. Now the network piece of it is the same. So the A is the same because Phoenix College, all of these college departments belong to the same network, but we want to give them their own granularity so that all of the end devices in administration belong to one network. All of the end devices in the IT department belong to the same network. College enrollment to the same network. So here's what I'm going to do. A001::64. So now I have used all 4 hex values. So I have now got myself up to the 64. 16 plus 16 is 32, plus another 16 is 48, plus another 16 bits, that is 64. All right, so I'm going to just do a little shortcut here. Oops, I don't like that. 2001 0CAD B023 A002::64. 2001 0CAD B023 A003::64. Now let me just go ahead and do what the address would be. Okay, so this is me looking at an end device and assuming that I'm going to do static addressing instead of auto configuration and dynamic addressing. So the whole first part, remember, is the route is the global routing prefix plus the subnet ID. So all of this part stays the same because remember, all of these PCs belong to the same network. So this would be 0CAD B023 A001. Now I'm going to go : and I'm just going to say like 10/64. If we go back to how many hextets there are, 1, 2, 3, 4. I see 5 hextets. That means this double colon represents 3 sets of zeros. Okay, so that would be an IP address for the Phoenix College administrators. What could be an IP address for the Phoenix College IT department? 2001, let's see, A002, because it needs to belong to the IT department, : and again, I can say whatever I want. I'm going to say A/64, okay, because I'm statically assigning it. And this is the unique host. This is an end device. So as long as it's a unique address, it'll go through. It'll be just fine. 2001 0CAD B023 A003, because this PC belongs to the enrollment office, : and I'll just say the 10 again. Okay. The last 64 bits are all the unique IPv6 addresses. It's the unique host portion. Okay, so Glendale 2001 0CAD B023 B001: :64. 2001 0CAD B023 B002. It needs to have a unique network. 2001 0CAD B023 B003. Okay, again, so notice here, this is Glendale College. All these departments belong to the B network, but each department has its own unique piece of the subnet ID so that they belong to their own LAN, their own network. I'm just giving my end devices an address, a unique address. Now, in the world of IPv6, just like the world of IPv4, I can set up static configuration where I'm manually entering the IPv6 addresses, or we can do auto configuration. I have another video about auto configuration because there's a few different ways to auto configure addresses in the world of IPv6. Oops. And 64. And then lastly, Mesa. Okay. And again, it would be exactly the same. I'm just going to shorten this a little bit, right? And I would give it a unique address, but it's going to have this 2001. Let's see if I can copy this. There we go. It has to come from the same network so that it knows where it belongs. Seems like it's as fast to just type it. Okay. All right. I hope that this helps. Remember, subnetting, we are going to use the 4th hextet. I can do it however I want. I just want to follow whatever my company's policies and procedures are. That's all for this example. Next up is the IPv6 address types. IPv6 is really unique because it has all different types of addresses. Now, IPv4 does too. There are a few more in IPv6 though. That's one of the things that makes IPv6 very efficient and adds some security. And there's just a lot of things we can do with IPv6 that we cannot do with IPv4. I always like to start this out with asking a question. Does IPv6 use broadcast messages? I hope you answered no to that. That's one of the differences between IPv6 and IPv4. IPv4 uses broadcasting, whereas IPv6 doesn't. It does not have a broadcast address. There are actually 3 types of IPv6 addresses. The first one, and the one that we're actually going to spend the most time on, is unicast addresses. Remember, unicast is a one-to-one. So I'm writing an email, I'm sending it directly to you. It's just a one-to-one connection. There are 6 different types of unicast addresses, and that's what we're going to talk about mostly. They are unique. Most of them are internet routable, not all of them though, and you can configure them statically or dynamically. Also, there's multicast addressing. We're familiar with that. Remember, multicast is a one-to-many. So for example, if I have 20 computers in my classroom and I want to be able to send a message to half the class, that half of the class will belong to a particular IPv6 multicast group. And maybe the other half of the class would belong to another multicast group. That would allow me to do a one-to-many. And IPv6 makes really good use of multicast addressing because they don't have broadcast addressing. Lastly is an address called an Anycast address. Now, this is a unique IPv6 address that can be assigned to multiple devices. So in other words, one address assigned to multiple devices. a packet that would be sent to an Unicast address is routed to the nearest device. So it's like a first come, first serve. There's 5 devices. They all have the same address. Someone sends a message, sends a packet. Whichever one of those 5 devices get that packet first is the one that will handle it. Now, I'm not really going to talk more about Unicast addresses because they're beyond the scope of anything that we need to learn in our Cisco classes. But if you move into IPv6 or you work for a company that does IPv6, at that time you may need to learn more about it. Remember I said there are 6 types of IPv6 unicast addresses. Let's take a look at those. There's a global unicast address. That's a globally routable address, similar to the public addresses in IPv4. There's a link local address. And I want you to pay attention to the word local. That means that it is not an internet routable address. It works on your local link. So it's similar to like a private address or an APIPA address. It never leaves the local network that it is assigned on. Number 3, a unique local address. Again, notice the word local. Okay, that means it never leaves its local link. It will not route over the public internet. It will not be publicly routable because of that word local. Number 4, a loopback address. As you know, in the IPv4 world, that's a 127.0.0.1 or a 0.0.27, right? And it's used to ping yourself, to ping your own device. Number 5 is something called an unspecified address, and that is a :/128. I'll talk about that a little more. And number 6 is an embedded IPv4 address. This embedded IPv4 address is used when you're running both an IPv4 and an IPv6 network. So our unicast addresses: global unicast, link local, unique local, loopback, unspecified, and embedded. Let's break these down. First of all, the global unicast address. This is the address that's going to be assigned to hosts and end devices. They're all going to be unique, and they are globally routable over the internet, over the public network. Now remember, in the addressing structure, we learned that an IPv6 address is made up of 3 parts: the global routing prefix, the subnet ID, and the interface ID. In a global unicast address, the first 3 bits are going to be 001. 001. That is the designation that it's a globally routable prefix. Okay. Now it can range through 2000, okay, which is 0010, or 3FF, because I can turn on I can turn off all the bits in the network, or I can turn them all on. So that's what gives us that range, okay, of 2000 through 2001. Now, for the most part, I've only ever seen 2001 public IPv6 addresses. Maybe one time I saw a 2000. The most popular, though, is 2001. And here's an example: 2001 ABCD 1234 1B34. This is the part of the address that is the global routing prefix and the subnet ID. So this could be any range between 2000 and 3FF. So we could have a 2005. We could have a 2020. Again, I've only ever seen 2001. One of the reasons we've gone to IPv6 addressing is because there are a gazillion of them. So even using the 2001, we've never used them all up. That's why we're continuing to see and use mostly the 2001. This would be similar to our IPv4 public address. The next kind of address is the link local unicast address. This is an incredibly important address in the IPv6 world, and the one on the CCNA that you're the most likely to see questions about. So it's a good idea to make sure that you completely understand the link local. You know what it looks like, what it's used for, why it's used, etc. Remember, I said link local. So that means it only works on the local network. Okay, it doesn't go outside of its own network. It's going to communicate with other IPv6 enabled devices on the same link, which is another way of saying the same network. Every device creates its own link local address. It does not have to be assigned manually. You do not need a DHCP server. It automatically gets an IPv6 address. So in other words, if you have a device that's IPv6 capable, it will generate its own link local address. And that's true whether it's a router, whether it's a computer, a tablet, anything that's doing IPv6 is going to generate its own link local address. Now this address is similar to the APIPA address in the IPv4 world. Now remember, the APIPA address is that 169 address, where if I turn on my computer and I'm running IPv4, but I'm not connected to a DHCP server, my host, my end device, is going to generate a 169 address because it wants to have an address. It wants to be able to communicate, so it self-generates. In that way, a link local address for IPv6 is similar. Now, the range of link local addressing is going to always start with an FE, and it's going to be an FE80 through an FEBF. And notice here that it's a /10. That means that there's 10 bits that are being counted, okay? So that is F, that's 4 bits. E, that's another 4 bits. So we're up to 8. And then 80, 10, through FEBF. Let me show you an example. If you were to do an ipconfig all on your command prompt, you're going to see this link local IPv6 address. Now notice here it's FE80 : so that's a bunch of zeros, 748B, B340. So this is an auto-generated link local address. And this is on an end device. This is like on a computer. The other place that I said it will auto-generate is on ports, your interfaces on your router. Here's my router. Here's fast Ethernet 00. Notice it's up. Now, I do have a statically assigned IPv6 address on this, 2001, DB8A, AAAA, so that's statically assigned. But notice here, FE80. This is the dynamically or the auto-configured link local address that the device's interface self-generated. This one did as well. This fast Ethernet 01 FE80, we can see right there, it self-generated its own link local address. Okay, so it's really important that you remember that every IPv6 enabled device is going to self-generate its own link local address. Another thing is I can statically assign a link local address. If I want to, as the network administrator, to put my own statically assigned FE80 : 1 : 10, I can do that. I can let it automatically auto-configure, or I can statically assign it. The next address is called a unique local unicast address. I like to talk about these together because, again, this is local, so it never leaves its local link. A unique local unicast address is used for local addresses within a site or between limited number of sites. This is not globally routable. This will not go out on the public internet. This is similar to IPv4's private addresses, like a 192.168 or a 10 or a 172.16 address. Okay, I, as the network administrator, could say, you know what? I want this classroom and this classroom to have a private, a unique Unicast IPv6 address, and that would allow these two classrooms to communicate with each other and not be routable on the internet. Now, that's not to say that that device wouldn't also have a globally routable address. It probably does. But if there is a reason as a network administrator that I also want these end devices to have private IPv6 addresses that are not routable, I can do that. It's important to memorize these ranges. The range for a unique local address is FC00. So in other words, 11111100. And they're a /7. So all of the other bits in that IPv6 unique local will just be randomly generated or statically assigned. This range goes through FD. Okay, so remember, C is 12, D is 13. So it's going to go FC00 through FDFF, and they are a /7. Both of these are not routable on the internet. What does a unique local address look like? Here we've got this, it says temporary, and that's because it's a private address that's being manually assigned, or it can be dynamically assigned as well. So let's take a look. Notice here, FDBE. So the minute I see that FD, I know that that is going to be a unique local unicast address. So if you were to get some sort of a question that gives you that address, it'll be like FD, blah, 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 blah. And it says, what kind of address is this? You're going to want to know that an FD is a unique local address. Same type of question, FE80, what kind of address is this? You're going to want to know that's a link local address. Okay, these addresses are private IPv6 addresses. They never leave their local link. They never leave their network. Number 4 is a loopback unicast address. Number 5 is an unspecified address. That's the :/128. And number 6 is something called an embedded IPv4 address. So let's look at these closer. The loopback, that's used by the host to send a packet to itself. It's testing the TCP loop, right? The TCP stack. It's represented with a ::1/128, or you can just type ::1. So this is like when you're pinging yourself, right? You're testing your own address. Now, an unspecified address, we're not going to go into this very much because we don't really see this very often. This is more something that's relevant to IPv6 routing. It's similar to the gateway of last resort for IPv6 or the default route for IPv6. This is when all 128 bits of the address are set to 0. So the IPv6 address would be 0:0:0:0:00. You get the idea. Or you could write it as just :/128. And this, again, is more something that we see when we're talking about routing. So we might talk about it again if we do a review of IPv6 routing. Lastly, an embedded IPv4 address. So an embedded IPv4 address, this is used if I'm trying to run an IPv4 and IPv6 network together. There is a time when I would have to take the packet and embed an IPv4 address inside of the packet so that the data can move through the OSI model, so that the data can go from the source to the destination. Here's an example of what this might look like. So here's our IPv6 network, okay? And if I need to, and again, this is really deep stuff that we don't need to know for an entry-level Cisco job or for a CCNA, but you want to understand conceptually what it is, and that it is an IPv6 unicast address. So here's my IPv4 address, 192.0.2.33. Now, what we would be doing here is I would be embedding this IPv4 address into the IPv6 address so that the PDU, so that the data can move through our network. Okay, those are the 6 types of unicast addresses: the global address, the link local, the unique local, the loopback, unspecified, and the embedded IPv4 address. I want to just recap the importance of a link local unicast address. Remember, every IPv6 enabled network interface has to have a link local address. It self-generates. And it doesn't matter if it's a WAN link, a LAN link, an end device. If it's enabled for IPv6, it will have a link local address. And these link local addresses are usable between the devices that are on the same network. And they will often be used. So like a router connected to another router will use the link local addresses to share router information, to share routing information. The range is FE80::10. The first 10 bits look like this: 1111, 111010. Everything else, it's up for grabs. It can be anything. And then through the FEBF. So FEBF, okay? That is our full range. Here's our last graphic. FE80, right? And then the remaining bits are just automatically generated, and then same goes with the interface ID. It can be automatically or manually configured. That's the end of this IPv6 review.